Lesson 7-2, Hooke's Law and Simple Harmonic Motion. Imagine a mass or something heavy hanging from a spring. If it just hangs by itself, it's in the equilibrium position, just hanging there. But if it's stretched and released, it'll bounce up and down. It bounces up and then down, and then up and then down and up. And it'll look like that. So it goes down and then up and then down and then up. That is simple harmonic motion. The middle line here would be equilibrium. And then that would be the amplitude, the height between equilibrium and the highest or lowest point. If you remember from our chapter on forces, Hooke's law, it gives the force of the spring, which was negative kx. Force was F. X is the distance it's displaced. K is the spring constant, and it's negative because it's always pulling the opposite direction of the distance. It's always pulling towards zero distance. So it's always pulling down or towards equilibrium. So the force will pull the mass back towards equilibrium all the time. But as the mass gets back to equilibrium, it's been moving, so it has momentum, so it'll just keep on moving until the force gets too high, and then it stops, and then it gets pulled back the other way, and then the force increases, and then it goes back the other way. Because that stretched spring can do work, there's energy in it. It acts over a distance. Work is done. It's the potential energy of, or the elastic potential energy. We called it the spring energy or spring potential energy before. Is 1/2 kx. Again, k is a spring constant, depends on the individual spring, and x is the distance. A Nerf dart gun uses a spring to launch a dart. If it takes 24 newtons of force to compress the spring 6 centimeters, what is the spring constant? Well, we have force, and we've got some sort of distance, which we probably make into meters. So our force is negative kx. So 24 newtons is negative k. Oh, we're supposed to find that. And our x is 0.06. Now, that displacement's negative because when you squish a spring, you're pushing it that way, but the force is always the opposite direction. So that's why there's a negative there. And why I've made the displacement negative. Divide those, and you end up with 400 newtons per meter for K. Now, how much potential energy does the spring contain? Well, our potential energy for a spring, or elastic potential energy, is 1/2 kx squared. Our K is 400 newtons per meter, and our x is 0.06 meters. You can put the negative if you want. Once it's squared, though, it'll become positive. And when you multiply all that together, you could get 0.72, and it'll be Newton times the meter, which is a joule. Now think about a string. If one part of the string is pulled up, well, Let's make it go up. Then the next little bit of string has to be pulled up, which then pulls up the next little bit of string, which then pulls up the next little bit of string. Because you can't just pull a little bit of string like that. It's connected, so it all has to be pulled up. That, oh, then that piece, and that piece, and that piece, and that piece, that makes the wave pulse. Because it was pulled up, but it's an elastic potential energy, the elastic force, sorry, that, and it pulls it back down. So it got pulled up, and then, but the elastic force pulls it down. Hooke's law makes it pull back down towards equilibrium. The more force, the quicker the string accelerates back, and the faster the wave will travel. So because of that, we can come up with a formula for the speed of a wave on a string. And it depends on the medium, so it depends on the individual string. For a string, that speed depends on the tension, which we'll call F, or force, and the linear density, which is mass per unit length. So it's the mass divided by the length. And your speed then is the square root of the tension divided by the linear density. So just think on a stringed instrument, the high notes, the high are very thin strings, and they have small linear density, and they're under a high tension. So we have high tension, small linear density, makes for a very high speed, which makes a very high pitch. The bass strings are usually wrapped, or at least much thicker. So for the bass, they have a higher linear density, and they're under a smaller tension. So it goes a slower speed, which makes a lower sound. All right, back to the simple harmonic motion. That's motion that regularly repeats. So that was the weight on the spring, and it, remember, was bouncing up and down. And it'll keep bouncing up and down. It turns out that the frequency is completely independent of the amplitude. That means the further you pull it down to release it, that doesn't change the frequency at all. In fact, it turns out that the period, and thus the frequency, only depend on the mass that's hanging there and the spring constant. So the period is 2 pi times the square root of the mass divided by the spring constant, or the frequency is its reciprocal, 1 over 2 pi times the square root of k over m. If the graph of position versus time of a simple harmonic motion is made, a wave is formed. It'll look like a sine wave. In fact, it'll be a sinusoidal function that we use to map that with. So if you think of a point on a string, some distance, call it distance x from the origin, and we want to know the vertical displacement of any particle at a given time, the wave repeats and it'll look like a sine. Or your book chooses to use cosine, which is just sine but shifted 90 degrees. So your function will be y equals a cosine of 2 pi t for time and the capital T is the period and the A is the amplitude and y is the vertical displacement. interesting thing here is if we pick a point on the graph and we don't move side to side, it'll just be bouncing straight up and down. So if I pick there, it just goes down and then back up, down and then back up, down and then back up. The other thing about this is if you use your calculator will need to be in radian mode. If you don't know how to do that, look it up. Usually go to mode or settings, and you need to change your angle measurement to radians instead of degrees. Let's say a wave has an amplitude of 1.5 centimeters and a speed of 20 meters per second and a frequency of 100 hertz. Write the equation of the wave position of the wave. Alright, well, we have y equals a cosine of 2 pi t over t. Alright, the amplitude's easy. You could leave it in centimeters. I'll just change it to meters, so that's your amplitude. But we need our period. Alright, well, frequency is 1 over period, or if you like, period is 1 over the frequency. So 1 over 100 is 0.01 seconds. So it'll be 2 pi t over 0.01 seconds. Well, we could simplify that a little bit. We could combine that. Two divided by 0.01 is 200 pi t. And there you go. At any given time, you know where the wave is. Again, if you were to use your calculator to graph it or do something with it, you'd have to use radian mode. These problems harmonize with the lesson. To be ready for the next lesson, read 17.1 and 17.2 from your textbook.